In the previous video, we applied the Dickey-Fuller test to the AR1 model, but we can also apply the test to the AR model of any lag, so we can just apply it to the ARP model. And if we do that, we call it the Augmented Dickey-Fuller Test, or ADF. And the null hypothesis in the ADF test is the same as the Dickey-Fuller test. So we test this coefficient on the lagged level of the y variable, and if we cannot reject the null hypothesis of the slope being equal to 0, then we say that the y variable has a stochastic trend. And if we reject the null hypothesis and adopt the alternative hypothesis of delta being negative, then we say that yt is stationary. And if we find that we cannot reject the null of stochastic trend, then we continue working with the differences, because the differences should be stationary. And whereas we work with the levels, if we reject the null hypothesis of a stochastic trend and adopt the alternative hypothesis. And what you see here in the augmented Dickey-Fuller equation is that the change in y is modeled by the intercept and the lagged value of y and these differences. So these lagged differences, and you have p minus 1 lags of the differences. So if you have 5 lags in your ARP model, then in the augmented Dickey-Fuller test you have 4 lagged differences, and you have the level here, of course. It is important to notice that this delta yt is the change in yt. So if you have yt on the y-axis and you have t on the x-axis, then the change in yt is equal to the intercept. So this is the drift. So this is the drift, and if delta is equal to 0, then this change in yt is explained by the drift and the changes in the previous period. And what you get is often this pattern, or if you disregard the stochastic bit or the random bit from the ut, you would often see something close to a straight line because of the drift term. And in economics, you also have the alternative. Let's see. The alternative view of the yt here, and we have t here, and we saw in a previous video that often in economics we have this exponential growth, and if you kind of work with this exponential growth pattern, then you have to account for that in the Dickey-Fuller regression. So this might then be thought of as a deterministic trend. So this curvature is the deterministic trend, and the intercept here is the linear bit of this upward trend. And the curvature is then captured by this deterministic trend. So this is a deterministic trend. So you see that as time increases, then the change in YT also increases. And so this is something you should include in your regression if you work with this exponential kind of data or price process, for example. So this Dickey-Fuller regression with a deterministic trend has the exactly same null hypothesis as the Dickey-Fuller regression without the deterministic trend. So the augmented Dickey-Fuller T-stat is just the delta hat divided by let's see here, the standard error of the delta hat. Okay, so this is the augmented Dickey-Fuller statistic, which is just the t-statistic from the augmented Dickey-Fuller regression. And the null hypothesis is that of the population delta being equal to 0. And the alternative hypothesis is that the delta is less than 0. The question now is, how many lags in this Dickey-Fuller regression should you include? And you include the number of lag lengths based on the Akaike information criteria or the Bayesian information criteria. And the Akaike information criteria often returns more lags than the Bayesian information criteria, but that is in general no problem. So if they show a different result, then often people choose to follow the Akaike information criteria. As I mentioned earlier, the ADF statistic, the augmented Dickey-Fuller statistic, is just the delta hat divided by the standard error of the delta hat, which is the t-statistic of the, or in the augmented Dickey-Fuller regression. But the statistic is not t-distributed. Okay, so it is not t-distributed, so we need a different set of critical values. And we have a one-sided test because we would only reject the null hypothesis of a unit root, which means that we have a stochastic trend, if this t-statistic or this augmented Dickey-Fuller statistic is below 0. So if the delta is below 0 by an enough margin, then we can reject the hypothesis of unit root. So the critical values depends on the significance level here, and it also depends on whether you only have the intercept or you have the intercept plus the time trend, the deterministic time trend. So if your t, or not t, but if your ADF statistic is below this value, then you can reject the null hypothesis. So let's see if I can actually write this correctly. Standard error of the sample delta. So if this number is more negative than the critical value, for example 2.86, if you have only the intercept in your model and no time trend, and you choose the 5% confidence interval, no, the 5% significance level, then you reject the null of unit root, and you can use the model in levels of y because it's stationary. But we have to throw in a word of caution, because we are just doing a hypothesis test. So if we get a value of the augmented Dickey-Fuller t-stat which is above the critical value, then we are not rejecting the null hypothesis of non-stationarity, which means that we should use the we should model the changes and not the level of the y variable. But this does not mean that the null hypothesis is true. Based on our data, we can just say that we do not have data which rejects the null hypothesis. So we might end up with rejecting the null hypothesis if we get more data, for example. But if we cannot reject the null hypothesis, then we have some indication that there is non-stationarity in our process.